Welcome to video 3 of my series on how to perform FM modulation and demodulation using the Python 2 programming language. In the previous video, we covered how to write a Python program that encoded information by varying the frequency of a sinusoid. In this video, we will write a program that reverses what we did in video 2 to get back our original information. To accomplish this, we will take each sample that is stored in the array YC that was produced from this equation and then work backwards to retrieve our information. The first task in working backwards is to undo the sine function's part in generating any of the samples held in YC. To do this, we need the Python equivalent of a calculator's inverse sine button, so let's head over to the Python console to take a closer look. We need to find the sine of at least one angle before doing anything with inverse sine. So as you can see here, I'm just going to find the sine of the angle pi over 2. Just hit the enter key to get the result. Great. Now that we have produced the sine of an angle, let's see if the inverse sine function gives us our original angle back. I am just going to go ahead and copy the previous result and then paste it here. After pressing enter, you can see that we got the equivalent of pi over 2. Now that we have seen how arcsine reverses what the sine function does to an angle, we need to remember that this here is also an angle, or I should say, an array of angles that is indexed by TS. Knowing this, I should be able to produce an identical array of angles by feeding the signal stored in YC into the arcsine function. Let's plot it out to see what we get. Well, here's the result. The question is this even correct? The only way to know for sure is to compare this set of angles that was just plotted here to the original set of angles that produced YC in the first place. Just to make what we're doing a little more clear, I'm going to grab the original set of angles from here and then assign them a logical name. Now that we have clearly defined our two sets of angles, we can overlay the both of them on the same graph like so. Let's take a look. Oh, that did not turn out at all. It is clear what should have been two identical sets of values do not even look close to being so. But before coming to any assumption about that, we need a way of taking a closer look at this graph. Fortunately, SpiderPython provides zoom and panning features when looking at plotted data. To activate the zoom and panning features, open the Tools menu and then click on Preferences. On the Preferences form, select IPython Console. Click on the Graphics tab and then select Qt5 from the Backend dropdown. To apply the changes, click on the Apply button and then click OK. All that's left is to reboot the Spider software. This is actually necessary for the pan and zoom features to become fully activated. Now that Spider is back up and running, you can see that the graph that was up before is of course gone. So I will just click the play button to bring it back again. Ah, this is easier on the eyes. As you can see, the graph has its own window, which is nice because you can actually resize it. To use the zoom ability, just click on the magnifying glass. You can zoom in on your plotted data like so, and if you didn't exactly zoom in on your desired spot, just click on the pan button to move the graph around. Well, this is interesting. It seems at least a small portion of the two sets of angles line up after all. Keep in mind that being interesting isn't enough, because you're not left with any actual hard numbers. But again, Spider has a tool to help us out. Well, here it is. Whenever the cursor is moved around the graph, its exact XY position is provided. Keep in mind that the cursor does not actually lock onto the plotted functions, so it is best to zoom in as much as possible to get a good enough approximation of whatever your coordinates of interest are. In our case, the interesting coordinate is the spot where both sets of angles diverge from each other. If you look at the Y coordinate, you will notice that it is approximately 1.57 radians, which is roughly pi over 2 or 90 degrees. This is really interesting because watch what happens when I pull out a calculator. Calculate the sine of 90 degrees, and then inverse sine the result. As expected, I get back 90 degrees. Now watch what happens when I do the exact same thing, but with 91 degrees. Alright, now let's see if applying inverse sine to this value gets us back to our original 91. And look at that. Instead of getting 91, we have a value of less than 90. This is a problem, so it's time for a solution, and that solution is called the unit circle. A unit circle is a good representation of all the degrees from 0 to 360. Most importantly, it is a great visual tool for solving our problem. Let's investigate. When investigating, I feel it's good to compare where your expectations went as expected to where they didn't. The area that is colored blue represents where everything went as expected. I am going to call this region Quadrant 1, where the white areas represent where PyLab's inverse sine function was not able to reproduce the expected results. These regions are to be referred to as Quadrants 2, 3, and 4. Now that the layout has been explained, I should mention that this unit circle has an extra ability. It is set up to do the task that the inverse sine button on a calculator would normally do. For example, if I calculate the sine of 45 degrees, this is the value that is produced. Watch what happens when our unit circle, with its inverse sine ability, eats this value up. Look at that. We got back our original 45 degrees. So as we just witnessed, if the original angle is anywhere in this blue region, the inverse sine function works just fine. This is why PyLab's inverse sine was able to reproduce the original angles in this region. But what about angles that fall within quadrants 2, 3, and 4? This is where using a visualization can really help out. Let's say if I calculate the sine of 122 degrees, and then feed the result to the unit circle, I get back 58 degrees, not the value of 122 that inverse sine would have produced if it had been truly successful at reversing the earlier operation. To get around this problem, all that needs to be remembered is that a half circle contains 180 degrees worth of angles. This unit circle already told us that 58 of these degrees have already been used up. So that leaves us 122 degrees from the 180 that was originally available. Look at that. This is the angle that inverse sine should have provided. As long as we know that the angle that we are after falls in this blue region, this trick can be used. Let's implement this into code. We just learned that the inverse sine function does return a correct value. We just need to categorize each of theta's angles by quadrant so that a simple offset can be made. This is the game plan. First, I'm going to draw a portion of the modulated signal YC. The time from where the signal starts to where it starts to repeat itself is called the period. YC's period is calculated by taking its frequency value and plugging it into this formula. Before continuing any further, I really want to emphasize that what's inside these brackets is just an array of angles indexed by time. Considering that I have the same array of angles just below, labeled as original theta, I am just going to give this a more consolidated feel. With it now extra obvious that theta, or I should say original theta, is what's plugged into the sine function to produce YC, I can relabel YC's horizontal axis as theta. Now I will break up the graph's horizontal axis into intervals of 90 degrees called quadrants. These are the same quadrants that I was talking about earlier when introducing you to the unit circle. With the horizontal axis now representing angles, we can see visually, at least on this diagram, which of the sine function's angles belong to which quadrant. Here's the thing. In each quadrant, I've only labeled 2 angles, where theta, of course, holds more than that. This brings us to the next task of calculating how many angles are in each quadrant. To do this, a couple facts need to be understood. The first being that all angles held in theta are indexed by the time values held in the array TS. Second, the time that expires from one angle to the next is defined by the sampling period. Third, the total time that must expire to produce 4 quadrants, or 360 degrees worth of angles, is defined by the period. Finally, if you count how many times larger the period is than the sampling period, you will have calculated how many values are needed to make up the full 360 degrees. From here on, I will refer to this number as n. As for the angles per quadrant, since each 360 degrees of angles is divided evenly into 4 quadrants, we just need to divide n by 4 to get the number of discrete angles that fall within each quadrant. Knowing the number of angles per quadrant allows us to keep track of what quadrant we are looking at for any given angle. For example, if there is 25 angles per quadrant, then we know that the first 25 values stored in theta represent quadrant 1 of the unit circle. Enough talking, let's put this into code. First, I'm going to give this set of angles a logical name. Afterwards, starting with the very first angle stored in theta, I am grabbing a quantity of angles defined by NQ. As you may remember from the unit circle, ArcSine did not have an issue producing these values, so there isn't a need to do any math on them. Before getting our quadrant 2 angles, I need to point out that there are different types of numbers in a programming language. For our purposes, we are only concerned about 2 of them. All the numbers that we have looked at throughout this tutorial are floats, but now we have to consider another type called an integer. For Python, any value that is used for indexing must be an integer. With NQ being used for indexing, you can use the int function to cast any value it receives to ensure that it's an integer. In regards to indexing, things are about to get a bit more complicated, where my previous explanation on how the indexing works with the square brackets will not be good enough. So, I'm going to display the first 5 values that are stored in theta. Here they are, and this is how these values are addressed, or in other words, indexed within the array. Just to drive the point home, I'm going to do this again, but I will change the first index value inside the square brackets. This is the effect doing so should have on the array. Let's see if that's correct. Just as expected. So if I compare what was just produced to the values from last time, you can see that just like last time, the values stopped outputting at index 4. Keep in mind that index 4 is actually the 5th location in the array. This is an important concept going forward. Again, the 5 I just highlighted with my cursor points to the 5th element in the array. If this was a 6, it would point to the 6th element in the array, which happens to be index 5. If NQ was pointing to the NQth position in the array theta, then we know that the next index, which would be index NQ, would not have been copied into the quadrant 1 array. With there being NQ samples per quadrant, this would ensure that index NQ will point to the first sampled angle of quadrant 2. With each quadrant having the same number of samples, from now on, you can take for granted that the first and last sample in a quadrant has an index that is a multiple of the previous quadrant. You can see that this is the case when looking at the arrays for quadrants 2, 3, and 4. Now that the first 360 degrees worth of angles from theta have been categorized by quadrant, it's time to offset each angle, which will finally solve for its value. Afterwards, we can take each angle and solve for ym. As you may remember from earlier in the video, any angle that is 90 degrees or less lined up with the original angles. These angles we have successfully solved for, but as for angles that are more than 90 degrees, this was definitely not the case. This is where the unit circle had come in as a visual aid. From there, we had learned that if you know that your angle should be in quadrant 2, you just subtract the value that Pylab's arcsine function produces from 180 degrees, and then you're left with the angle that you had originally expected. As for the values that have been classified as quadrant 3 angles, the same formula that was applied to all the quadrant 2 angles works just fine. All that's left is the angles that have been classified as quadrant 4. The solution for these values is to add 360 degrees to each angle in the quadrant. All that's left is to stitch these 4 sets of angles back together. Just paste in order from least to greatest each quadrant of angles into the hstack function like so. And of course, we need a good logical name for this new array of angles. Before continuing, I need to make really clear that we have successfully solved for the angles that went into producing the first cycle of the signal YC. But that is only the first cycle of many. How many cycles? We can calculate that by taking the length of time that we are simulating for, and then by multiplying that value by the frequency of our carrier. Back when we had first looked at YC at the beginning of this video, it was really obvious it had many cycles. Doing what we just did to solve for the angles of each of these cycles is impractical. Fortunately, Python allows you to place a task into a loop, which will repeat until whatever condition you specify is met. Whenever dealing with loops, I've always found that in the end, that it makes things much easier to flowchart out my thoughts with just pencil, paper, and English words. To maintain some continuity, I will write onto the flowchart that we determine the total number of YC cycles. That brings us to the next task of setting up the loop, where we must repeat the task of solving the angles for each cycle of YC as many times as necessary. So, how many times are necessary? Well, the answer to that is as many times as there are cycles. This is why from now on, we need to keep a tally for each time that we solve the angles for a cycle. As long as the tally is less than the total number of cycles, we know that there are more cycles that we need to solve the angles for. Back over to Python, I will use the variable cycle to store the starting tally. You will notice that it is already set to 1. That is because we already calculated the angles from YC's first cycle up here. Just as was stated on the flowchart, as long as the tally is less than the total number of cycles, we know that there are more cycles that we need to solve angles for. Let's go ahead and assume that the answer is yes. 2 is the current tally, less than the total number of cycles. This would mean that we have many more angles to solve for. To do this, we need to know the first and last indexes for the 4 quadrants that belong to the cycle that our tally is pointing to. Remember that each angle is stored in an array, where each stored spot has an address or index to call it up by. Here's how we can go about calculating these addresses. We already know that for cycle 1, that the index that points to the first angle in the second cycle would be indexed by NQ times 4. For now on, let's call this value the cycle start index. Let's jump ahead a bit and say that we just solved for all the angles for whatever cycle. Each time that a cycle's angles are solved, we need to calculate a new starting index for the next cycle. To do this, all that needs to be remembered is that n defines the number of angles per cycle. This means that we only need to add n to our cycle start index in order to know the first index for the next cycle. Now it is time to set up the start and ending indexes for each quadrant of our current cycle. We can almost do it exactly how we did it for the first cycle. One last thing, since quadrant 2 and 3 angles are solved with the same formula, I can get away with combining them as one super quadrant. This does mean that the super quadrant will have double the angles. Finally, we are almost ready to move on from setting up all this indexing, but first, we just have to look after the quadrant 4 indexes. Just always remember that the end index of the preceding quadrant is really the first index that doesn't point to one of its values, but instead points to the first value of the quadrant that directly follows. With the starting and end indexes conveniently laid out for each of theta's 90-degree quadrants, our next task would be to use those quadrant circle formulas from earlier to fix each angle based on which quadrant it falls in. With that last comment outlining what we're about to do, it's time to solve for those angles. Of course, we will start with writing out the formula for the quadrant 1 angles. Like last time, we can just take the quadrant 1 angles as is. What's nice is that we don't have to calculate any of these indexes inside the square brackets, since we just did that beforehand. As for quadrants 2 and 3, we just need to subtract whatever is stored in theta from 180 degrees. As always, Python works in radians, so 180 degrees converts to just pi. All that's left is to write out the formula to fix our quadrant 4 values, which we can fix by adding 360 degrees to the appropriate values in theta. Just like before, the degrees must be in radians. That works out to double of pi. This is almost great, but is not quite right yet. If you look at the angles that make up YC's horizontal axis, you can see that after the first cycle, the degrees do not reset back to 0, but instead, they keep incrementing to larger and even larger values. Again, this is just another problem that will have to be solved, because let's say that arcsine must provide the angle for a value of 0.5. For now, let's make the assumption that we have already ensured that we're only considering quadrant 1 values. This will guarantee we are left with 30 degrees in every case. This is great for our first cycle of angles, but when looking at cycles 2, 3, 4, and onwards, we can see that 30 degrees does not fit at all with the angles that were already present on the horizontal axis. Luckily, this is not that big of a deal, because this is a problem that can be solved in 3 simple steps. So here it goes. Step 1. For each cycle, we will assign a number that will represent a different multiplier of 360 degrees. Step 2. Well, as for step 2, I will just go ahead and do the multiplication that was hinted at in step 1. All this multiplication has produced a distinct offset value for each cycle, which brings us to step 3. This is where we take the arcsine angle for each cycle and apply its corresponding offset value that we just calculated in step 2. After all this hard work, all our values from theta will now fully match up to the values held in original theta. Putting these ideas into code is nice and easy. Just remember that the first cycle that was produced up here did not require an offset. So that is good. No changes there. As for the second cycle, we now know that each angle would need an offset of 360 degrees. For the third cycle, it would be 720, and for the fourth, the offset would be 1080. Remember that Python works in radians, so for our 360, I will add 2 pi to all the angles. But this is also a loop, which means any code embedded inside will repeat, and each time that it repeats, we will be calculating the angles for the next successive cycle. Now, as for the cycle that succeeds the second cycle, which of course would be the third cycle, we would need to change these 2's to 4's to get the correct offset. Obviously, we can't do this as the program is running, so instead, let's replace this 4 with a variable that can be updated as the program runs. As things are at this moment, our new variable isn't holding anything, so let's have it hold our initial value, which was 2. Again, 2 is fine for the first cycle, but when this block of code is run the next time, we need the 2 to be recalculated as a 4. This is great, because all we need is some addition. So after this line of code has been run, and the loop runs this block of code again, the value sitting in pi multiple will already be 4, giving us our 720 equivalent. After that, we will get a 6, which will give us our 1080 equivalent, and so on. With our angles corrected, it's now time to use the hstack function to combine the quadrants into a cycle's worth of angles. With that done, we need to add the current cycle's worth of angles to the angles that we have already produced. For the question, is our tally equal to the total number of cycles? The answer will always be no, unless we remember to add a 1 to our tally before the loop gets to ask the question again. If this block of code is run enough times, then our tally will eventually equal the total number of cycles. When the tally becomes equal to the total number of cycles, the answer to the question inside the diamond shape will be no, so Python or any other programming language will exit the loop. This brings us to the very last task of algebraically solving for ym. But before doing so, I would like to do a sanity check to ensure that we actually produced all these angles correctly. The best way to go about doing this is just to plot out a graph with the original set of angles that went into producing YC in the first place, alongside the angles that we have just recreated. If all is good, the recreation should match up with what we originally had. I am just going to run this now and see what happens. Look at that. We have an error message. It's saying that indices must be integers. With indices being plural for index, we know that either of these indexes, or even both of them, do not happen to be the integer type of value that Python requires for indexing. What is really handy about Spider Python is you can just head over to the console and find out, like so, what type of value is held in a variable. As for the reason why I checked out cycle start index first, is that it's not only the value that gets transferred to a dependent variable, but the type of value as well. This is important because, as you can see, quadrant 1 start is totally dependent on cycle start index. Here's what is interesting. The cycle start index is initially dependent on this formula. Obviously, 4 is an integer, and if we check out NQ, we can see that it is an integer as well. So what happened? The answer to that is we know that cycle start index was initially an integer, but it had to have been changed somewhere along the way, and here is the likely culprit. To see if this is the case, I'm going to head over to the console to see what type of value is held within n. Look at that. It's a float. If n is a float, then the result produced by this formula is a float as well. And since the value from this formula gets stored in cycle start index will also be a float. With our entire problem being that n holds a non-integer value, we need to make n an integer value, just like we did earlier with NQ. Keep in mind that integers can only represent whole number values, so anything on the right-hand side of the decimal will be lost. As you can see, n doesn't have any non-zero values on its right-hand side, so this isn't a problem. Enough talk. I'm going to go ahead and convert n into an integer here. I didn't do this inside the loop, because when dealing with loops that loop a large number of times, it's best to keep as much outside as possible for performance reasons. Let's try viewing our two sets of angles a second time. Well, this is definitely closer, but our two sets of angles still don't match up, so it would be easy to assume that there is something that is just plain wrong with our demodulation scheme, but this isn't the case. The issue is actually a quite interesting conceptual problem portrayed in most telecom textbooks. This is done for the purpose of illustrating that FM modulation works by shifting frequency. For the same reason, I had portrayed the final result of the modulation that we looked at back in part 2 of this series, with that same widespread in frequency as well. Here is the problem with that. If your shift in frequency is a significant percentage of the high-frequency carrier's base frequency, you probably won't be able to extract your original information. How do I know that frequency shift is even the problem? Well, take a look at these three graphs. The top graph is the original information that we desperately want to extract from the middle graph. As for the bottom graph, that's the two sets of angles that should match up with each other, but don't. Here comes the proof about the encoded signal's frequency shift being the problem. Watch as the information signal gets weaker. You can see that that middle graph has less and less frequency shift, and best of all, our two sets of angles that should have matched up become closer to matching. This brings me back to this critical moment back in part 2. Watch this scene. The last thing I need to do is assign values to both the center frequency and the modulation factor. For now, I set the modulation factor to 15, the only reason being that it forces the signal stored in YM to have a really visible effect on how much the carrier's frequency varies. Here we are going to do the opposite, since we now want as little variation as possible. Look at that. We have a perfect match between theta and the original theta that produced YC in the first place. Using this formula, we will finally be able to solve for YM. If you are interested in how this formula was derived, I will provide a link in the description below this video. Keep in mind that all we have done up to this point is calculate theta for every given value of YC. So, now I'm going to divide each value of theta by what you see highlighted in blue. Of course, we need to pay attention to bed mass, so everything that we are dividing theta by must be between these brackets. Here I'm going to start by typing out 2 times pi. Now I'm going to grab our time from up here, which is TS, And finally, I will multiply all this by the modulation factor. With that done, we just need to take the center frequency divided by the modulation factor and then subtract it from this mess here. All that is left is to assign all the demodulated values produced by this equation to ym, giving us our original information that we originally encoded back in part 2. Let's go ahead and plot this. It seems we have half our original information back, but that any of the data that was negative in value isn't being reproduced. If our solution retrieves positive values beautifully, but not negative values, we can just simply rejigger our data values to be always positive by adding an offset. Now, it doesn't functionally matter, but I don't like the fact that I've named the original information signal and the demodulated information signal with the same name, so I'm going to fix that right now. Great. With that being a bit more clear, I'm going to go ahead and see if our information signal has finally been extracted from our carrier in one piece. That's better. Now all we need to do is subtract that offset. So for now, I can just do that subtraction here. Let's see how that turned out. There we go. As expected, everything has been shifted down by 1. In other words, we have finally recreated the original information signal by decoding it from the varying frequency of YC. Before wrapping this up, I want to mention that any code from this tutorial can be found over on my Github. Other than that, this brings us to the end of this 3-part tutorial. If you have watched all 3 videos, you are well on your way in understanding how electronic signals can be simulated within software. If this video in any way succeeded in helping you with a tricky concept, please click the like button. Until next time, goodbye.